All right. So what we're going to cover in this talk is the camera object, some stuff on star particle rendering, and finally the fisheye camera renderings. So first, the camera object. So what does the camera contain? What the camera contains is knowledge of the data source, your simulation, the rendering geometry, that is, where are you looking from and where are you looking to. It contains the transfer function that you're going to use while you integrate the volume. And finally, it'll contain the resulting image plane. What does the camera allow you to do? Well, luckily it comes with a bunch of helper functions. So you can use this once you've created a camera to say, look at a new center with some north vector. You can use it to switch the entire view where you change the looking direction, which is the normal vector, the width, the center, and the north vector. Now, I've mentioned the north vector twice. I guess we haven't really covered this. The north vector is the vector which, when you have your resulting image, it will look in the up direction. And so if you specify out of your XYZ volume that you want the north vector to point in the Z direction, that means when you get the final image, up will be that Z direction. It'll be parallel with that vector that you specified. So you can use that, say, if you wanted to, if your data set was laid out in a particular direction that you'd like, you can choose it to be an X direction or some other direction, or an arbitrary 3 vector. Okay. So you can use these helper functions like switch view and zoom. Zooms you in by some factor. So if you say zoom by a factor of 10, it'll zoom in by a factor of 10. If you do a zoom in, it'll give you a number of snapshots slowly zooming in over those number of steps that you have. You can then have a move to function which slowly moves your camera to a final location over some number of steps. You can also change the width while you're moving. Then other useful things are rotate, which is a single rotation, and then rotation, which is a set of frames that you slowly rotate over. Finally, there's the camera.snapshot, which is when you actually take the image, the rendering itself. These are all documented in the YT docs for the camera, and so if you want to know exactly what one of these arguments does, I would say go take a look there. So what we're going to do is take you through some advanced camera movement so that you get a feel for how to control these things. This is in your scripts directory of that repository that you just checked out, and it is the rot_zoom render, I think. What is it? Whoa. So yeah, rot_zoom render. And so this is what it looks like. What this is going to do is first load up the data set. Feel free to change it to something else. This is a small one so that it's easy to, it's fairly quick to render. You're going to specify the center as being at the center of the box. The viewpoint is coming from the 1, 1, 1 direction, so you're kind of looking down from the top corner of the cube. We're going to set the width equal to the square root of 3 so that you get the full volume of the cube so that the image plane sees the whole thing. We're going to use 512 pixels, and here we're going to specify an up vector, which we're going to use as our north vector of the script later on. Now, one way to pick out good transfer function values is to find the min and max in your volume and then set the contours up between that. So that's what I'm doing here, but with finding the quantities extrema of density. I'm then going to make that transfer function, and just this -2 and +2 pads it a little bit so that you don't run into kind of the edge of the transfer function. If you set that equal to MI and MA and you sample off of it, you might get some artifacts. So that's not too important, but it may be useful. I'm going to add 7 layers, and here I'm going to specify that my alpha of the transfer function, I want to be in a log space going from 10 to the minus 0.5 to 10 to the 0. Just something to choose. I'm also going to use this color bounds, call underscore bounds keyword here to specify that I only want to populate the transfer function between the min and max here. Finally, I'm going to create the camera. You've seen this already from Cameron's talk. In this example, we're going to specify that the north vector is up and that no ghost equals true. Finally, I'd like you to add steady north equals true. So go ahead and edit that if you get a chance. What steady north does is if you're rotating your cube or your data set and your north vector is not exactly orthogonal to your rotation axis, it'll keep the same face of the data set, the same direction of the data set, pointing in the same direction, so you don't get this like wobble effect. It's just a way to, it's just a aesthetic thing that I've found useful, some people don't. So then what this script does is it takes its first snapshot and saves it out. Or I guess in this case it maybe doesn't. Oh yeah, here it is. And then because I've written this script to work in parallel, I've put a few things in an if clause to make sure that only the root processor does some of this work. So first of all, I'm going to plot out the transfer function so we see what this thing looks like. Then I'm going to write this image to a file called myrendering.ping. Now, I'm going to do something a little bit tricky. Instead of the clip argument, I'm going to normalize the image by the image average plus some number of standard deviations above that average. And I'll save that as enhanced. I'll give you an idea of what that does. We'll come back to this enhancement of stuff later. Okay, so now at this point, it will have made one single snapshot of your volume. Now what I want it to do is rotate 360 degrees. Then I want it to zoom in on, say, the most massive cluster in my simulation, the densest point. And while it's zooming in, I want it to kind of change the, so it's going to both zoom and move to that center location at the same time. And once I get there, I want to rotate around that galaxy cluster one more time. Okay? So how do you do this? First, I'm going to set up kind of some values that I'm going to use later. First, I'm going to find where the peak density is. So that's going to return me the value and what I'm calling new underscore C. That's going to be my new center. That's my final center. Then I'm going to set the number of frames in each segment. It's going to rotate really quickly and zoom in really quickly, but this is done so you can do this on your laptop in a short amount of time. It's going to take 10 frames to rotate, then 10 frames to zoom in, and 10 frames to rotate again. And I want the final width to be 0.1. That's fine. Okay, so now I'm going to set up a counter called frame, just so that I can save out these images with a unique name each time. And now I'm going to start the rotation. So how you utilize this, this is one of these camera helper functions, camera.rotation, and that's specifying that I want to rotate 2 pi radians over R1 frames, so over those 10 frames. And what that's going to give me back is, and I'm going to use this enumerate to keep track of which one in this rotation I've done. It's going to give me back the number as well as the camera snapshot. And snapshot is going to be that NumPy 3D array of the image itself. Okay, so what's going to happen then is it's going to write out that image to this file, but only doing so on the root processor. I only have that in there so you can use this in the future on parallel processing and it'll all work fine. You don't necessarily have to have that kind of stuff. I'm going to print out some timing information just because I'm interested in that sort of stuff. The next piece I'm going to do is the pan and zoom. And so this is going to use another camera helper function called cam.moveTo. And I'm going to specify that I want to go to the new central density location over the number of frames that I earlier specified. And I want it to zoom in, so I'm going to give it this final width of 0.1, which I apparently didn't use my own variable from up there. And I'm going to do the same thing. I'm going to loop over these snapshots and save them out on the root processor. Finally, when I get to when I'm now zoomed in, I'm going to rotate again, just as we did before. And so I think on my laptop, this took about, I used it on 2 processors by doing mpi run-np2 Python, this rote zoom render.py -- parallel. And it took about 30 seconds or so. Hopefully that worked fairly well for you guys as well. Has anybody tried to run this and run it to completion? That's right. In this case, both of the processors would be working on each individual frame. They decompose the volume, and essentially one processor works on rendering half the volume, and the other process works on the other half. Okay, so you should get something that it may look slightly different from mine because I was playing around with these scripts like 2 minutes before the talk. But if you play with the transfer function a bit more or change something, it'll look like this, where it rotates the box, and then it zooms in on that cluster and rotates again. And this is a pretty small data set, so you're seeing some artifacts from the rendering because it's not resolved really at all. With a unigrid? Yes. So if you only have one grid, then you can only use one processor. If you have a unigrid simulation but you have multiple grids, then it's fine. So if you had run Enzo with 64 processors, you'd get 64 level 0 grids. You could still run with up to 64 processors. So did that work for everyone? Did anyone, did it not work for someone? Great. You guys have just made a 30-frame movie. Does anybody have any questions about the commands that we use to do that? Looks great. Yep, we're gonna get to the why that enhance works so well, but essentially what that's doing is renormalizing the RGB channels of the individual image to make all 3 of those channels pop. Okay. So this was showing that. Now I want to show you what's possible if you have great-looking data and you play around with these camera objects. The first of which is by Britton Smith. So this is from a galaxy or a unigrid WIM simulation that studies like the cosmic web and metal feedback. But what he did in that first part was rotate while the simulation evolved. And then what he's done is he's plotting the transfer function over here, and he's slowly moving the transfer function up in density value as he rotates this box, which is a really, I think, unique and cool way to visualize cosmic structure in this case. And this has a few little extra bits and pieces where he grabs the transfer function image. That's another helper function that I'm not going to cover. But I would imagine, I haven't seen the script that makes this, but I don't believe it would be that difficult. Britton can probably speak. So it's a fairly simple extension to what you've seen so far. It's just that this is running on a great, beautiful data set that has, I think, 1,024 cube cells. Another great example is from John Wise, and what this is showing is utilizing a galaxy formation simulation. utilizing a different transfer function called the Planck transfer function, which is an attempt to make photorealistic images using filters defined by a telescope. And so there's a few ins and outs of doing it. It's far too complicated of a transfer function that I think we should get into in detail, but it's fairly well documented, and I invite you to, if you are interested in doing that sort of render, contact us, email the group, and there's plenty of example scripts somewhere. Okay. Another thing that we can utilize in YT's volume rendering is looking at star particles, or particles in general. These don't have to be stars. This is the star_particle.py in your scripts. It will only, this example will only work with Galaxy 30, which is the isolated galaxy dataset. And it takes a little bit of time to run because it's a slightly larger dataset. But what you have to specify is essentially you have to collect the particles and get information about them, so you find out which ones are stars. This is based on finding out what the creation time. This is kind of an ENSO specific thing, but you essentially need to get NumPy arrays of the stars' position, and we're going to use their age to map colors. There should be a star_particle.py. Is that not true? Okay. In the repository that you checked out earlier, there should be a scripts directory, and inside that is star_particle.py. Galaxy 30 is the isolated galaxy dataset from the available data. You don't necessarily need to go through this example, but I wanted to show that you could do such a thing. You have to set up a few things that tells the rendering mechanism in YT when and where to deposit the particles and the kind of emission from those particles. So it sets up a KD tree so that it can do quick lookups to find out, as you're rendering through the volume, where these stars are. You can, yes. Number of stars. Yeah. It's expensive, but. Right. Right. Yeah. In fact, I took this from a script that if you didn't have stars in it, you could create a random set of some number of points, and it would deposit them. But what you would get out, if you run this, some of you may have completed running this, you get something that's this galaxy, and there's some stars in the center, and their colors correspond to how old those stars are. So it doesn't look that great because there's not a ton of stuff going on, but that's what's possible. And I'll just mention that we're looking to improve upon the way you do such a thing. And if you are really interested in rendering star particles or other particles, tracer particles, any particles, please feel free to get involved. We can use as many hands as possible. Okay. Now we're going to get into something that hopefully will allow you to show your beautiful renders on the Adler Planetarium Dome tonight. A lot of thanks goes to Mark Subarow for making this possible. And so what I'm going to do is go through and show you how to make such a fisheye camera where it's essentially as if you're sitting and you're shooting out rays along all kind of line of sight within like a 180-degree sphere. So the fisheye camera is defined by a few extra things. First is the field of view. Today we're just going to be showing 180 degrees so that the image plane that you get out will be everything in front of you, essentially. There's nothing stopping you from setting it to 360 degrees, but it starts to get a little bit confusing as to how the image is mapped to your simulation. You also define what your resolution is, and this is going to be the resolution across that field of view along the diameter. So you'd have a field of view of 180 degrees, and if you had a resolution of 180, each pixel would be a degree of the sky. Finally, you're going to have to supply it a transfer function. Now there's both a fisheye camera and a newly written mosaic fisheye camera. And we wrote this mosaic fisheye camera in the last week or so that we could split up the possible 8,000 by 8,000 squared image plane into multiple images and not kill our supercomputers or even laptops. So what this does is it's going to split up the image plane into NIM-X and NIM-Y images in the X and Y direction. This is very useful for creating these huge renderings because otherwise you'd have to store that image plane on every processor that you're using to make this rendering. This mosaic fisheye camera does require one extra thing. Instead of just doing a snapshot, you also have to say save image so that it pieces those images back together. But this all allows you to do multi-level parallelism, so you have a huge data set and a huge image plane, and you can do it in something less than a month. So there's a few things that I want to go over before I let you loose on this scripts. The controls for controlling the parallelism are NIM-X, NIM-Y, and procs per WG. WG is a work group. And so what this will do is for each individual image plane, procs per work group will work on that on the entire data set and do the projection into that image plane. This sets up MPI subcommunicators for anyone who cares. What values should you use for these? It really depends on your data. If you have a huge image, you want to split up the image plane into a large number of NIM-X by NIM-Y sub-images because your image starts to be a huge source of memory use. If you have a lot of data, you have a 512 cubed or 1024 cube data set, you're going to want to use a lot of procs per work group so that you can split up that data between that many processors. A few notes, still procs per work group should be a power of 2 just like we saw in the regular renderings in parallel. I'm hoping to fix this in the somewhat near term so that it can be arbitrary. And advanced things would be considering the processor and node topology of the supercomputer that you're using. Perhaps putting one image on each node of your supercomputer or one on each socket of your computer. Anyways, that's very advanced stuff that we probably won't have to worry about right now. So I want you to open up example_fisheye.py out of that scripts directory, and I'm going to run you through what it's doing in there. Okay, so this is going to load up this DD46 from Enzo Tiny Cosmology just because the fisheye is a little bit slower of an operation because the vectors that you're integrating aren't parallel to each other, so there's some nasty math. We're going to make this a 512 pixel image, and what we're going to do is set this equal to the domain right edge, and actually I want you to go in there, I modified this in a later thing, and do 0.75 times pf.domain right edge. So that's going to put your camera at almost the corner of the box, so that you're just barely kind of inside the box. Then you're going to set we'll show you later on where the focal center down here, which is going to be put right at the center of the box. So this is going to be at 0.5. So what you're going to have is a camera looking from 0.75, 0.75, 0.75 to 0.5, 0.5, 0.5. So it'll be looking through that direction. Okay, so we're going to do some usual things like find the min and max the density so that we have an idea of what to render. This is this focal center, which is what the fisheye camera will set up as being in front of you. Or if you're in a planetarium dome sitting backwards, lying on your back, it's going to be what's directly above you. I want you to modify another thing in here. I'm going to set the number of contours that we're going to add to this rendering to 100 so that it's really smooth. So now comes the invocation of the Mosaic fisheye camera. We say cam is Mosaic fisheye camera. We give it these arguments: the center, the radius, the field of view, and the number of pixels. The radius is how far out from your camera center that the rays will integrate. So I think I've set this to hopefully to 3 or something large. Oh no, okay. One more edit is just change the radius to 3 so that we go through the whole box. In Enzo, this is a unit of 1 would be the full width. Just go through the whole thing. Sorry about these last changes here. So then you give it the transfer function. You specify the focal center. If you don't do that, it'll take your camera center and set up a direction for you, but it may not be the direction that you necessarily want. So keep that in mind. We're going to give it a few things that we might like, and then here's where you specify, if you were running on multiple processors, here's where you'd specify how many images you'd split it up into and how many processors you'd want to work on each work group. Then we're going to take the snapshot and save out the image. So has anybody run this and gotten something beautiful or ugly? I can tell it's taking a little bit longer than normal. We're going to Is anybody running it right now?
Yeah, it looks fine.
So since this was only developed last week, you can either update your YT installation now, or the module on Nautilus should be updated to include this. Yeah, you should be able to do it just with YT update. Yeah, this is hot off the presses, so to say. You should end up getting something that looks like this. Folks getting something that looks kind of like this? Still counting. I cheated. I had the image pre-made. If it's going really slow or making your laptop catch on fire, maybe try reducing the number of pixels. Correct. Yeah. Thanks. Here's the latest version of the script if is that not showing up? You can go to this paste if you want to download the latest script. Are people getting images? Go, Matt. What's the fastest way to get to the non-stable version of YT? Okay. Anna. So now you have a starting script for making one of these mosaic fisheye images. Feel free to now use it on your own data, either here or remotely on a more powerful computer, and make some images to show tonight if you feel like it. Yeah. I'm just checking. I have no idea how long this is supposed to go till. A while ago, I guess. I want to show you guys one more thing on the on this enhancement. So this is kind of touching up your images. What you may find is that there's some flicker that occurs between frames if you're rotating or you're doing a time evolution of some data. I'm going to skip through this, but the nice thing you can do is kind of use an enhancement like they do in the movies. So in that scripts directory, there's an enhance.py script. And what you can do is do Python enhance.py, then like star.ping in whatever your rendering directory is, and then give it a folder to pipe those images to, like enhanced. And what that will allow you to do is for each color band in the RGB, it'll calculate the mean and the standard deviation of the image. It'll then renormalize the entire image to some combination of those two values that make it look aesthetically pleasing. And then it clips those values to between 0 and 1 because you can get out of bounds stuff. But it's a nice way to make your images look really nice. So if I did it in here, I'm going to do, I'm going to remove my enhanced directory and run Python enhance.py rot zoom star ping enhanced. And it's going to go through and it's going to enhance those images. And now these look pretty cool. So this is the same rotation and zoom in that I showed you before, but now some of those colors are popping quite a lot more. So as a kind of ending note, we didn't have too much time to fit this into any other part of this workshop, but utilizing some of the same framework that's used in the rendering, you can create streamlines of your data. There's a stream test.py in that scripts directory. Feel free to take a look at that. But in this example, you're running 200 streamlines that start out at random positions in the box and follow it for some code unit length of 1 using the x, y, and z velocity of the data. And you can visualize them in Matplotlib using the axes 3D object. I'm not going to go into it because it's a little bit out of context, but I wanted to say that this capability is there. One more thing is that if you have an individual streamline, it acts just like a YT data object, and so you can access fields along that streamline, so that if you say get a streamline and you want to know what the density is along that streamline, you can access that. If you want to know what the magnetic field line strength is along that streamline, you can access that. You can make streamlines of magnetic fields. You just have to define a vector field for it to calculate the advancement of the streamline. You cannot do that yet. It's something we would love to do. Yeah, the question was, can you plot these streamlines along with a rendering? That is not currently possible unless you really take care of what the looking vector is and kind of merge them together. Jeff? It's on. So talk to Jeff and poke and prod him until it's possible. Nathan, did you have a question? Okay. So what I hope you've learned is the camera object is very powerful. For pretty movies, you may want to enhance them. And I've given you an idea of how to manage this multi-level parallelism for huge renders, and there are streamlines. Thank you.